Hi. In this video, I do want to continue the work on the timing, but I've got several updates as well that I want to get into. There's a couple of other small little things that I've done off camera, and I want to give you an update on those. But more specifically, the primary focus today is going to be getting into the load, increment, and decrement timing and reshaping that control signal. So let's get into that.
Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey.
Okay, update number 1. I promised at the end of the last video that I would take and replace the counter ICs on the additional 2 registers that were tested and report back if there were any issues related to that. Absolutely surprisingly enough, I was able to replace these counter ICs with the faster version, and both registers tested out perfectly the first time. I'm not going to argue with success here. These are now back to the state that they were in, except they are actually using faster counter ICs, so I should be able to improve and fiddle with the timing related to that on this control circuit. Update number 2. I was able to get this EEPROM replacement working. Now this is the one that has the relay in it. The one that has the NPN transistor in it still bleeds enough current to try to power the rest of the board, and this battery is pretty much dead at this point. So how did I fix this one? Well, turns out I think I probably hurt this IC, and you can see I've got kind of a, let's see if I get the angle right here. I've got a bit of a question mark on there. Once I replaced the IC in here with a new one, it worked perfectly right out of the chute. Update number 3. I did manage to get a number of these, not solder-less breadboards, but they call it a solder-full breadboard, meaning that I can take this circuit and drop it onto here and likely have everything I need in order to make this work, and then I'll just solder in some jumper wires and what have you. Now the challenge with using these is the size. So if you look at this in the way that I have the control logic breadboards set up, what you'll see is that it encompasses both power rails as far as the size here. And so if I just, instead of having one power rail in between each one of those modules, if I change that to have 2 power rails in between each module, then I should be in much better shape here as far as the width is concerned. I should be able to solder all of this onto here and get it established into the breadboard appropriately, and likely have to deal with a little bit of coverage here. Maybe I'll set it up in such a way that it hangs over this way and just slide it out a little bit. I'll have to play around with that a little bit to determine exactly how I want to use this, but this is the next step in the evolution of these EEPROM replacements. All right, getting into the timing issues and how I want to now shape this load increment decrement signal. What I'm showing you is what my clock looks like and my inverted clock, and then what the typical control signal is going to look like. The current load increment and decrement takes half the clock cycle, and the business side of that is the rising edge that happens going back to a high level at the end of the signal. And that's the point in time when either the load is actually committed, the increment happens, or the decrement happens. And the key that we've identified at this point is that we want to pull that rising edge as close to the start of the clock cycle as we possibly can. And we can do that by a rising edge detector, which is typically just your clock signal ANDed with an odd number of inversions of that clock signal. And since the inversion takes a small amount of time to take place, it's usually pretty easy to get some kind of a spike signal. Now, I want to NAND that with my control signal for this. So it's going to be the load increment and decrement shortened into just a rising edge detection on the clock, NANDed with the control signal. And what that's going to give me is it's going to give me a passive high signal, but an active low signal that then returns high. And at that return to the high signal, that's when the load, the increment or decrement would occur. And then with the latch happening at the falling edge of the clock or the rising edge of the inverted clock halfway through the clock cycle, that's going to give me a much better timing consideration. I should be able to then, in theory, shorten my clock cycle, or the distance, the time between my rising edge and my falling edge of my clock. Or put another way, I should be able to increase the speed of this CPU. That's ultimately what I want to try to get to. Let's see how fast we can get that signal to take place. What I have here is I've got just a simple 555 timer that's been set up to oscillate. Not going to get into this. It's not going to be part of the build. This is just part of my test circuitry. I did manage to go and get some 74HC04. Now this is the same logic series I'm using on the PCBs. So my timing should be much more accurate with these. And I'm going to start replacing the control logic with HCs. So I'm going to drop that in here. I'm going to set up power and ground. And then if I take my output and tie it to one inverter, that'll be a second inverter. That'll be a third inverter. And now the output of this is one side of my clock here. The other thing, I'm going to stick this here. The other one I'm going to add is a 74HC08. Now this is a 2-input AND gate. And again, I'm going to do power and ground, where this becomes one input into the AND gates. This is my triple inverted. And if I take the clock natively and put it into the other side of that, this signal here now becomes my spike. This is my rising edge detector and falling off as quickly as it possibly can. So this is ultimately, this is what I want to measure here. All right, I'm going to break in here for a moment. This is where my inexperience comes into play. And the next 6 minutes or so, give or take, of video are of me with a bad assumption related to the low threshold for input voltage. Unfortunately, I was looking at, in the datasheet, the 74HCT193 counter IC, and I really have the 74HC193 counter IC that I'm using in my build. And I didn't realize I was looking at the wrong thing. Unfortunately, they've got them buried in the same datasheet, and I wasn't paying that close of attention to it. So you'll see me refer to 2 volts as I go through this next section. Now the reality is I need to get that to below 1.35 volts, give or take. And so what I'm going to have to do is I'm going to have to actually put this into the build and test it to see exactly what's going to happen. You see, here's the other error that I made. I didn't remember that I've got a 74HC138 demultiplexer sitting in between the signals that I'm testing here and the counter IC. So it's totally irrelevant what the outputs of this are relative to the counter IC, because I've got a different IC that's in the middle of it. I could go on and on and on, but the reality is I just need to get it into the build and see exactly how many delays I need to put into it in order to get the right delay. That does not look like it is giving me anywhere near a high enough signal. I say high enough, meaning I don't believe it's giving me the spike that I need. So if I add 2 more inverters, I'm now up to 5 inverters. That's still not giving me quite what I need. That looks like it's well within CMOS logic tolerances for a high value. Okay, so for HC logic, anything that is over 2 volts is considered to be high. So what I've got is I've got that lined up This turns into a bit of a mess too, trying to calculate the width of that spike and whether or not it's high enough. If you look at the actual spike, it is about 4.5 volts high. Each division is 1 volt. Vertical division is 1 volt. So that's clearly big enough to take the signal from low to high and then back to low again. This then would allow the load increment or decrement to take place as appropriate. But once again, I've got that 74HC138 sitting in between. So what I'm going to do is I'm going to cut this here, and I'm going to jump ahead and start pulling this back together and see if I can make some sense of what I've been trying to say here. Hang with me, please. Okay, I believe this now puts me back on track. The last thing to do is I actually need to AND my rising edge detector, rising edge spike, if you will, my spike signal. I need to AND that together with the actual control signal itself. This is going to be coming off the EEPROM. And right now I've just got it represented with a one input of the gate pulled high, where the output of that now becomes the signal that is going to go off to the 74HC138 demultiplexers. What that should do is that should allow me to have an increment, have a load, have a decrement take place, and then return back to the do nothing state relatively quickly, affecting that increment, affecting that decrement. The load happens in parallel, but it's locked at the rising edge. So I'm calling that the business end of it, if you will. And so this then should become, well, not this part, but this should then become part of my clock shaping in my control logic. And what I need to do is I need to replace that board. It's got a lot of the controls on it right now for the main bus asserts. So I'm going to have to go through another control logic cleanup. Not all in one video, but let me rebuild how that clock, inverted clock, and now spike clock signals are then they travel to the rest of the circuit for usage. Let me get the build out. Okay, I'm zoomed in on the build quite a bit here. I need to replace part of this, and really what I want to do is I want to add this breadboard right in this space. But everything that crosses this divide has to be addressed in some way, shape, or form. Power and ground is not going to be a big deal, but these are signals coming from control logic up here. So for the moment, what I'm going to do is I'm just going to start with a fresh breadboard down here. I'll tie it into power and ground and get that dealt with. This 74LS86 is used as a buffer and an inverter for the clock signal. And I'm not able to get 74HC86. They are no longer produced and cost prohibitive. So I ended up getting a 74AC86, which is slightly faster, but should not create too much of a problem. Now I'll pull power and ground directly off of this build. And then my clock signal itself is this line right here. So this is the clock that's going to become the input here. And then this jumps it from one set of gates to the next set of gates. Now, this low, which was the second input for the first gate here, this turns this first gate into a buffer. This high over here turns the second gate into an inverter. Now my output, which was here, is going to have to be replaced. And this output over here, which was for the inverted output, that's also going to have to be replaced. I want to get those over here to the leftmost row or column, however you want to look at that. Okay, so now that will give me a clock up the left side. Here is my inverted clock, which I will take up the column right next to it. And so this third column here will be my spike. Now, to shape that spike. So on my little prototype here, I actually used 5 of the 6 inverters on this 74HC04. Let's see if I can't get some decoupling on here right away. I'm going to take the inverted clock as input, which means I only need 4 additional inverters. Okay, what this now does is that gives me 6 inverters all wired up in series. And so this is inverter number 1, this is inverter number 2, and then its output here could go over to drive this. So I have inverter number 1 as part of the 74 AC86. 2 and 3 gives me my odd number of inverters. And then coming down here, this is the next inverter, and then up here, this is the next inverter here. This could be another point if I wanted a different delay. And then down here for the next to the last and the last inverters up here. So that gives me this point here. Effectively, every other one of these here, here, and here are opportunities to take that signal off to the bus line here that I'm planning on putting up here. So I'm going to mark this with a Sharpie. My intent is to put it into the PCB this way as well. Did pick up some 0 ohm resistors, which will be used to jump stuff together. The next one is I needed to AND that with the actual clock itself. And again, I'll get power and ground. I will put in some decoupling. And then I have opted to use this top gate up here. So let me pull the actual clock over. Okay, and then the final pull of wire is the output of this AND gate back to my signal bus. The final thing I can do here is I'm going to take clock and hook it up here to clock, inverted clock, and hook it up here to inverted clock. And then I've got this signal that runs off someplace, but this was my original clock coming off the build itself. So that's here. And what I want to do is I actually went to, I should be able to take it from there. Now I just need power and ground. And this IC is not used anymore, so I'm just going to remove it to prevent confusion. And then I should be able to test. So power. That's not quite working right. There's my load. There's my value to load. There's my load up there, but I'm not asserting onto the main bus. Okay, so there's my load. This must not have been sitting down right. That looks right. I've managed to successfully break nothing. Let me do a little bit more cleanup here. I need some decoupling caps on the power rails, and I want to clean up the power on both ends of this. I'd love to make an attempt to get it in here, but I don't think that's going to happen. Okay, while I'm working on the cleanup, I want to orient you here a little bit as to how I wanted to tackle this cleanup and then the subsequent test. After thinking about it quite a bit last night, I decided I'm going to take this board and move it up here to the top. And what that's going to do is a couple of things. Is it's going to get this out of the way so that it don't have to deal with all of the rat's nest that's going on in here. But I do have an increment decrement load that's built into the Control 3 ROM, which I can then turn around and take advantage of in order to test my new delay. Okay, I think this is good. Let's power it on and see what happens. And I've got a short. No, I don't. I don't have it plugged in. Let's try it again. That looks reasonable. That looks reasonable. Let's go for broke. Okay, this is my R1 register, which is working. What I want to do is I want to duplicate this down here on R2. Let me break out the code, get that done, and I will reload my memory ROM. Okay, I made a copy of the test code from video 61 and changed all of the references from R1 to be R2. This is specifically going to be for testing the new timing of the increment, decrement, and load. But as I went to build everything, turns out I don't have instructions for decrement and increment that were already available. So I ended up having to add those into the assembler. And these are specific to R2. That also means that I had to create logic for them in the control ROMs. Basically, every ROM now needs to be updated, and I will get those into the build and we'll give this a test. Now, if I haven't mentioned it before, I'll mention it again. All of this code is available on GitHub, and I will have a link to each of these three projects, the test code project, the assembler project, and the control logic project, in the links in the description. Let me get these on the EEPROM and get back to the overhead. Okay, with everything reprogrammed, let me give this a shot here. It did not fetch the correct instruction. So for whatever reason, I am not fetching instructions. Or I have an off by one problem on one of my EEPROMs. That's the correct instruction there. Okay, good. That does not look like it worked. And that does not look right either. Okay, so the first order of business is to make sure that this code works on this register using the old circuitry, and I still have that hooked up here. So I'm just going to switch this back to the old clock and reset. And yeah, that is working. So this is now off the old clock, which has then been delayed several nanoseconds related to all of this delay here. So if I now take and move that back to the spiked clock that I have here, you can see that this is not working. Let me see if I can speed this up a little bit, or slow this down, I should say. So I'm looking to make that spike a little bit longer, and that has not done anything good. All right, so let me try another inverter here. And again, this is a 74HC04. So I'm going to take my most delayed output and move it over here to this one. And this output now will come back to where I had the clock plugged in. And this is now working. I'm going to start making a list of some of the things that I see as issues here so that I can start keeping track of them. Number one is because I've now shortened, well, expanded, but it's still relatively short comparison, the duration of this spike signal. I am not expecting to see load, increment, and decrement. These are the first three blue lights. I'm not expecting to see those show up on the R2 register right now. Number two, if I trace my clock signal, which is driving all of this new HC logic up here, if I trace that signal back down here, I'm coming off of a 74LS151. It's right at the bottom of the screen. And the LS high is not high enough to drive an HC input high. Number three, and probably most significantly, is I still have all of this delay built in here, and some delay built in down here, and some delay built in over here that I want to try to eliminate. The next thing to look at is the fetch register line drivers. These up here, which are driving the main bus, all of this HC logic over here, these are still LS, not HCTs. So I'm likely to replace these with a couple of HCT line drivers to make sure that my signals clean up over here. Okay, let's start with trying to clean up the clock here. So I've got it hooked up to the clock bus, which is running up the side here. It's associated with the red side of these power rails. But if you look at this, it's really kind of falling off, almost like it's got a capacitance associated with it. And at 1 volt per division, I'm getting just up to 3 volts, and it continues to climb up. I want to see if I can improve the shape of that signal a little bit, and I'm going to do that by pulling that out and then connecting my clock over. Well, that certainly improves the shape of that signal. And even as I get into 50 nanoseconds per division, the scope's not happy about 20 nanoseconds per division. So at 50 nanoseconds per division, I'm still looking at a pretty good rate of climb here, a little bit of overshoot, but that looks a lot better. That's more like what I am anticipating seeing. All right, let me make that change permanent. Okay, next thing to look at is the main bus assert from the fetch register. And you can see I've got 2 signals here. I believe one of them is coming off of R2 asserting onto the main bus, which would be this one up here because it is the HC logic. And the other one would be when this second light here is red. This is LS logic asserting on, and so it has a lower high value, and therefore that's the lower signal. Let's prove that. So now I've got the fetch register asserting out onto the main bus. And yeah, I've got the it says 3.8 volt, but the lower high value for sure. And then this is the assert main here. That would be this one. And notice it's gone way up. It's a far better signal up there. That almost, yeah, that's about 5 volts outputting. Because these are LS logic, I want to swap them out for HCTs. Okay, let's take a look at that now. And yes, the output is very much like what I would expect to see for an HCT signal. Change my trigger point. And this is 50 microseconds per division. I'm not sure where that odd trace is coming from. Nothing is asserting onto main. And whatever it is, it doesn't seem to be consistent. It seems like it's a timing issue. Almost like I've got conflicting things happening on main. Well, it is the main bus, so, but I'm not exactly sure what's causing that trace to drop like that. Yeah, I'm not sure what would cause that, but again, it looks like a capacitor discharge curve. Okay, after staring at this for a little bit, there's a couple of things I want to just quickly talk through. First of all, from where this curve starts to almost where it ends, 1, 2, 3, 4, 5 divisions at 200 microseconds per division. That's 1 millisecond for this signal here. And now, so this is on the main bus, the least significant bit of the main bus. 1 millisecond for that to actually come down to a reasonable close to 0 voltage. So I've always planned on doing this, but my fear is right now that I'm actually hiding or masking a problem. But I always had plans for a RZ pseudo register, which would be a 0 value. And my intent on how to do this was to pull each line of the main bus to ground with a pull down resistor. Now look what happened here. That gentle slope has become a much sharper turn. Now again, at 200 microseconds per division, that's of course going to look really good, but now as I get into 250 nanoseconds per division, I basically have 1 microsecond for that signal to come down. That's a lot better. It's not in the nanosecond range that I would like to see it. So that basically means that I need to put pull down resistors on this signal. Now, once again, I'm afraid I'm masking a problem here and not actually solving it. So this may come back to haunt me in the future. If you've got any suggestions on what to look at and what to test, let me know in the comments, please. Let me get these resistors hooked up. So yes, there's still a problem here. I'm not exactly sure what's going on with it, but at least I've got my pull downs in place up here. That should improve my success, but I don't know how to go about troubleshooting this, at least not at this point. Okay, I'm pretty happy with the progress so far. Getting a lot of these little small things that are creating big problems out of the way. Uh, that's a good thing to get those behind me, at least get them identified and some solutions. I still have something going on with the main bus that I got to get to the bottom of, but this seems like a very good pause because the next thing I want to get into is looking at the timings and the control logic. And if I start into that, it's going to probably turn into a rabbit hole. And I'd rather dedicate an entire video to that. So that'll be up next. In the meantime, see you soon.